Greetings everybody. This recording is going to cover part 1 of the Chapter 8 Lecture Notes. Chapter 8 deals with momentum and impulse and also center of mass. We'll worry about center of mass in some future lectures. So right now let's look at momentum. Well, we have linear momentum because there's also something called angular momentum, which deals with rotational motion, which we'll get to that in later chapters. So right now we're dealing with linear momentum, and we use a lowercase p to indicate momentum, and it's a vector, hence the little arrow symbol on top of it. And the momentum, so for an object to have momentum, it has to be moving with some velocity v. And of course the object has a mass of m, and the momentum is given by P is equal to mv. And remember, momentum's a vector. Well, because momentum's a vector, in general, it could have an x component, px is equal to mvx. It could have a y component, py equals to mvy, and a z component, pz is equal to mvz, where vx, vy, and vz are respectively the x, y, and z components of the velocity. But in general, even though the real world is three-dimensional, we'll mainly look at, when we do momentum in 2 dimensions, we're just going to deal with the x and y components. Well, the MKS unit of momentum is a kilogram meter per second, mass times velocity, or mass times speed. Well, we can write Newton's second law in terms of momentum. Remember, P is mv. Well, let's look at Newton's second law. The net force acting on an object is the mass of the object times the acceleration. Well, what is acceleration? Well, in the next line, acceleration is change in velocity over change in time. A is delta v over delta t. So Newton's second law, F equals ma, can be written as F equals m delta v over delta t. Now we're going to assume with these momentum problems that the mass of the object, or objects, you could have more than one object in the system, as we'll see. But we're going to assume that the mass doesn't change. Unlike, for example, a rocket problem, where if you have a rocket moving through space, it's burning fuel, and so the total mass of the system, the rocket and the fuel, that mass is changing because as it burns fuel, the mass gets smaller. But we're not going to worry about that. That's a little bit. You're all more than capable of doing it, but it's not really necessary. So we're going to assume that the mass of the system is constant. So we can write the change in momentum as, we can write delta P as m delta v. So look at Newton's second law. The net force is m delta v over delta t. Well, m delta v, that's your delta P. So we can write the net force as delta P over delta T. And that's Newton's second law in terms of momentum. That's just good to know, that the net force, meaning the sum of all the forces acting on the object, must equal the change in momentum over the change in time. F net is equal to delta P over delta T. Well, what is delta P? It's the change in momentum. The change in any quantity is the final minus the initial. So delta P is m, then parentheses, Vf minus Vi. And for now, we're going to stick with one momentum in 1 dimension. We'll worry about 2 dimensions in another lecture. So now there's something called conservation of momentum. In certain situations, the momentum of a system is conserved. And again, by system, we don't want to overthink it. It's typically one or more objects. And we'll see in this next example in just a second. But what happens is, when is momentum conserved? Well, if the sum of the external forces acting on a system is 0, meaning if the net force is equal to 0, then we have conservation of momentum. Well, what does that mean? Well, remember, and that's the qualifier, if the sum of the external forces equals 0, then momentum is conserved, meaning the initial momentum is equal to the final momentum. And by that, again, we mean the initial momentum of the system. And by PF, we mean the final momentum of the system. But that's when we say momentum is conserved, meaning P initial equals P final. But momentum is only conserved if the sum of the external forces acting on the system equals 0. And again, don't overthink this concept of what we call a system. Let's look at an example. Let's look at the example of an archer. So example 1. So we have a 60 kilogram archer, and he's standing at rest on frictionless ice, and he fires a .03 kilogram arrow horizontally, and he fires the arrow at a speed of 85 meters per second. We're neglecting air resistance, i.e., that there's no friction on the ice, frictionless ice, and there's no air resistance. Okay. Now, what does this mean by the sum of the external forces? If the sum of the external forces equals 0, well, we're going to get to that. Okay. So I want to know, after the archer fires his arrow, with what velocity does the archer move across the ice? And this is a conservation of momentum, because when he fires the arrow is going to have momentum in the positive x direction, similar to the recoil of a gun, if you will. The archer will then acquire a momentum in the negative x direction. Well, step 1 in our solution, the system is simply equal to the two masses involved are the archer, we'll call him M1, and the arrow, which we'll call M2. We'll assume that the bow is part of the archer, because he never releases the bow. He's holding on to the bow before the arrow is fired, and then he's still holding on to the bow after the arrow is fired. So very, very simple. Consider the archer and the bow to be the M1, because he never physically releases the bow. But after firing the arrow is going to go in the positive x. Hence, the archer still holding on to the bow, they will go in the negative x. But that's our system. The archer is M1, which will be the 60 kilograms. We'll call the arrow M2, which is the .03 kilograms. Now, momentum is conserved only in the x direction. And I'll put a little qualifier here. Why? Well, remember, in the x direction, this condition holds. The sum of the external forces is equal to 0. Why? Well, there's no friction on the ice. So there's no friction between the archer and the ice. Remember, if there were friction, if he were to slide in the negative x, Fk would act in the positive x, and Fk would be, the kinetic friction force would be an external force, and it would not be 0. But remember, no friction, so there's no Fk. Now, what about the air resistance? Well, when you fire the arrow in the positive x, the air resistance would act would oppose it. The air resistance would act in the negative x. Remember, air resistance is a form of friction. But again, there's no air resistance. So again, there are no forces in terms of the forces acting on the archer and the arrow, M1 and M2. There are no external forces in the x direction. They're none. So they add to 0. I mean, if there's none, then so momentum's conserved in the x direction. Now, in the y direction, momentum is not conserved, but we don't care about that because the external force in the y direction, there's the external force of gravity acting on the arrow. It will eventually cause the arrow to drop to the ice, but we don't care about the y direction. I just want to know with what velocity does the archer move across the ice after firing the arrow. And then typically with conservation of momentum, we always set up our initial condition and our final. Sometimes you'll see me write before and after. So here's the system. There's the ice. And then the system is the archer is M1. Just draw by this little man here, or person. It could be a man or a woman. But there's the archer, that person. Here's the arrow, the right there. Okay. Now initially the system is at rest because he's just standing at rest. So the archer is not moving, and the arrow's not moving. It's just standing there holding this bow and arrow. Now, so that's the initial, where that's the man or the archer, that's the arrow, and initially both M1 and M2 are at rest. Now let's look at the final. In other words, after he fires the arrow. Well, the archer is M1. He's gonna move, and again by conservation of momentum. If the arrow, which is M2, if the arrow moves in the positive axis, the archer is going to slide in the negative axis. So the archer's M1, the arrow's M2. So V1F, that's the final velocity of M1. The subscripts can seem to get a little bit cumbersome. It takes some getting used to, but we just have M1 is the archer, M2 is the arrow. V1F, that's the final speed of M1. V2F is the final speed of M2. So again, initial, that's before he fires the arrow. Final, that's what happens to the system after he fires the arrow. You can see M2, which is the arrow. M2 is moving in the positive axis with a speed V2F. M1 is moving in the negative axis with a speed of V1F. Again, don't let the subscripts throw you. V2F, final speed of M2. V1F, final speed of M1. Well, now remember, we know that momentum's conserved in the x direction. So we know that by conservation of momentum, which I abbreviate COM, conservation of momentum, I know that P initial must equal P final. Right? Right there. Anything conserved, meaning the initial is equal to the final. Well, remember the initial momentum, let's now go to the next line. The initial momentum is 0 because in the initial case, neither M1 nor M2 is moving. So I know right away Pi is 0. Now what is P final? Well, remember when we talk about initial and final, when we say if momentum's conserved, when we say P initial equals P final, initial means that's the initial momentum of each object in the system. P final, that's the final momentum of each object in the system. Well, again, initially, neither one has momentum because both M1 and M2 are at rest. But now P final, well, we know after he fires the arrow, M1 has momentum because M1 is moving, as indicated by V1F, and M2 has momentum because M2 is moving, as indicated by V2F. So the final momentum is M1 V1 final. That's the momentum of M1 plus M2 V2 final. That's the momentum of M2 after the arrow's fired. Again, initial means before, final means after. Okay? Well, what do I want? I want with what velocity does the archer move across the ice after firing the arrow? So I want V1 final. Because I know V2 final is 85 meters per second. Because remember, M1 is the archer, M2 is the arrow. He fires the arrow horizontally at 85 meters per second. That's your V2 final. I'm looking for a V1 final. So again, conservation of momentum, P initial equals P final. The initial momentum of the system is 0 because neither M1 nor M2 is moving before he fires the arrow. Then after did I say collision? I meant firing the arrow. The final momentum is M1 V1 final. That's the momentum of the archer plus M2 V2 final. That's the momentum of the arrow. Now just algebraically solve for the vector V1 final. Well, nothing complicated. Bring the M2 V2F term to the other side. It becomes negative. Then divide by M1 because we're looking for V1 final. So you get V1 final equals minus M2 over M1 V2 final. Well, we know M2 and M1. Remember, M2 is the arrow, M1 is the archer. So here are the values. V2 final, that's the 85 meters per second. Okay, so you get negative 0.0425 meters per second. Well, the negative is as expected, meaning look at my diagram. V1 final is in the negative x direction. which is what our calculation gave us. And this is good. And then I just happen to notice that, we know it's negative, but 0.0425 meters per second, that's 4.25 centimeters per second. So V1 final is equal to negative 4.25 seconds, which means it's actually, well, not actually, another way of writing it, it's 4.25 centimeters per second in the negative x direction, which we know from the figure, above. Now you could have reversed it. I could have drawn it such that he fires the arrow. I just did it because that's the figure there. Clearly, when he fires the arrow, it's going to move in the positive x, which means he's going to move in the negative x. Now you could have done it the other way, where where he would, if you had taken that picture and reversed it. What if the picture had been reversed? Well, it doesn't matter. You're going to get the same answer. Just the archer would be moving in the positive x. But that's that. But it's, again, momentum is conserved because there are no external forces acting in the x direction. Notice everything we did involved the x direction. Alrighty, let me go ahead and save this video and get it posted. In the next video, we'll do impulse. This is a good, what's called in the language of physics, a one-dimensional conservation of momentum